If you're into technology, you're probably familiar with YouTuber Michael Reeves and his incredibly hilarious and often pointless electronics projects. One of my favorite Michael Reeves videos is the one where he heavily modifies a Roomba robot vacuum to make it scream in pain whenever it runs into anything. After seeing this video, I immediately knew that I wanted to create one for myself because I found the entire premise of this project to be hilarious. Unfortunately, Michael didn't provide any documentation, code, or schematics for his Roomba, and other designs that I found on YouTube weren't as clean and integrated as I wanted, so it was up to me to figure it all out for myself. As you can see, I was successful after a good bit of experimentation, and I want to share my design in as much detail as possible so that other people can build their own screaming Roombas. Without further ado, let's get started. Let's start with a quick overview of the design. The Roomba is just a Roomba 760 that I got off of eBay for around $30, but any Roomba from the 500 series up to the 800 series should involve a pretty similar process. The Roomba doesn't need to work properly because we aren't really using any of the original mechanical or electrical systems at all. If you're ever unsure about the disassembly process for your particular Roomba, there are plenty of guides online on websites such as iFixit that should be able to help you. From the top, the vacuum appears normal, but when I flip it over, you can see the electronics situated in the area that was previously inhabited by the brush roll. The two motors are visible on the far left and right of this area. The Arduino that controls the vacuum and the MP3 player shield that plays the sound files can be seen on the left, and the motor driver board is mounted on the right. There are also some buttons mounted in this area that can be used to control the various functions of the robot. One of the buttons toggles between kid-friendly and adult screaming modes. Another toggles between the robot behaving autonomously and being driven by the user via remote control, and the third allows the user to select from slow, medium, or high-speed operation while in the autonomous mode. I initially wanted to use the original buttons on top of the Roomba to control these functions, but there wasn't enough room under the top cover to mount everything. We can take these 4 screws out to remove the bottom plate and battery door, revealing the remote control receiver and the left wheel well, as well as the lithium polymer battery that's mounted in the Roomba's original battery bay. That's pretty much all there is to it in terms of a high-level overview of how the Roomba works. Now that we've briefly gone over the design of the robot, let's take a more in-depth look at the design and go over all the steps required to actually build this thing. So the step that I want to start with, mainly because it's the most annoying, is routing input from the bumper on the front of the robot to the electronics bay on the bottom of the vacuum. This is a crucial step since the bumper is what tells the electronics when the robot has run into something. To start, take the bottom cover off of the Roomba by removing these 4 screws, and then pull the original battery out of its bay. We won't be needing it anymore since we'll be adding in our own battery later. Next, pull out the dustbin and then remove the side brush and wheel modules. I can't show the wheel module removal since I had to destroy them during the build process, as you'll see later, but it's just a few screws located around each wheel. Then remove the brush roll from the bottom of the Roomba by removing these screws and lifting it out of the device. Now we can start to take the top off of the Roomba to access the bump sensors. Start by prying off these 2 trim pieces as well as this third piece that surrounds the display at the center of the Roomba. Now remove the handle by sliding it toward the back of the vacuum. Next, pry this large trim piece off of the Roomba. You'll have to slide it back slightly after freeing it to get it off of the device. We can now pry this display cover off as well. Pull this piece of plastic off of the display and now remove these 20 or so screws that hold the top of the Roomba on. They're all the same length, so don't worry about getting them mixed up. Once the screws are out, lift the keypad off of the Roomba. Then flip the vacuum over and remove the bottom piece of the bumper by taking out all of these screws. I don't know why, but I always find removing these bumper screws to be particularly annoying for some reason. Now we should be able to slide both the bumper and the top case right off the Roomba. We're getting close, but there's still some more stuff to disassemble before we reach the bump sensors. Remove this daughter board by lifting straight up on it and unplugging the connectors on the bottom. Then unplug all the connectors on the main board, lift out this plastic protector, take out these screws, and remove the board from the robot. There will be some more connectors to unplug on the bottom of the main board once you get it out. Now we can finally see the two bumper sensor modules. Remove each sensor by taking out these two screws and pop the tops off of the modules by removing these little rubber bumpers and then prying on the 3 clips that surround each module. With the cover off, we can see how these sensors originally worked. The top part of the sensor emitted an infrared light beam, and the bottom part of the sensor received that beam as long as the robot wasn't colliding with something. Upon collision, this arm would move between the emitter and receiver, blocking the beam and signaling to the main board that the vacuum had bumped into something. Since I didn't know the specs of the emitter and receiver, like what voltage they expect and the characteristics of the receiver's output, and I didn't really feel like finding out, I just went for this simple and somewhat stupid looking solution. I took a tactile push button switch, soldered some wires to it, and glued it into the housing such that the arm would press it whenever a collision occurred. While it may look dumb and unreliable, it actually works really well. Once you've soldered wires to your buttons and glued them in, route the wires down through the hole where the battery terminals used to connect and into the battery bay. Then drill a hole through the wall separating the battery bay from our electronics bay and feed the wires through it. Use stranded wire instead of solid core wire to make things a lot more flexible and easier to deal with. Now that the bump sensors are done, we need to do one more thing before putting things back together. Route the wires from the Roomba's internal speaker down to the electronics bay. This is the speaker that will play the screaming noises once we get everything set up. You might be able to wedge a larger speaker into the dustbin if you want the sound to be louder, but this tiny internal speaker seems more than sufficient to me. Find the speaker connector and insert 2 wires into it, routing them out the back of the main board area and down into the electronics bay. Now glue the connector down so that the wires you inserted don't ever slide out in the future. We're finally done with most of the annoying Roomba disassembly and modification, so you can follow all the previous steps in reverse order to put the Roomba back together. However, make sure not to install the wheel modules, brush module, dustbin, bottom cover, or battery, since you'll just have to take them right back out again in future steps. Now we can move on to the second most annoying step, the motors. I could have just used the original wheel modules as they were, but I wanted the Roomba to be able to move a lot faster to make things more exciting. I ended up using these two 20.4:1 12-volt high-power metal gear motors with a 25mm diameter from Pololu. I also made sure to buy 2 of their mounting brackets for 25mm motors, as well as 2 of their universal mounting hubs for 4mm shafts. Links for the parts and files that I use in this project can be found in the video description. For maximum authenticity, I wanted to use the original Roomba wheels, so we need to get those out of the wheel modules before we continue with mounting the motors. This involves taking the cover off each gearbox and then hammering out the shaft that holds the wheel in place. The shafts were incredibly stubborn in my gearboxes, so I ended up having to destroy them to free the wheels. Once I got the wheels out, I drilled 4 holes around the center of each wheel and then attached the universal mounting hubs to the insides of the wheels using M4 by 15mm machine screws. With these mounting hubs installed, we now have the ability to connect the original Roomba wheels to our new motors. But before we do that, we need to actually attach the motors to the body of the Roomba. This part was challenging for me to figure out because I was worried about both getting the height of the motors right and ensuring that they were firmly attached to the Roomba itself. I ended up 3D printing 3 parts in order to properly attach each motor: a 35 by 25 by 21mm block and 2 L-shaped pieces that provide further support to keep the motors from breaking off. If you don't have a 3D printer, you should be able to make these parts out of wood or a similar material fairly easily. First, I used hot glue to attach the 2 blocks on opposite sides of the electronics bay so that they were in line with where the original wheels were located. Next, I cut notches in the plastic walls between the electronics bay and the wheel wells that are the same width as the 3D printed blocks in order to allow the motors to protrude from the electronics bay to the wheel module areas. I also had to cut some notches in the bottom plate because otherwise the motors would be too tall and would keep this bottom plate from screwing back on all the way. After cutting these notches, I attached the motors to their mounting brackets with the included screws, and then used a combination of hot glue and epoxy to secure each motor mount to the top of one of the 3D printed blocks. This setup might be sufficient by itself, but I was worried about the upward torque exerted on the motor by the pressure on the wheel, potentially ripping the motor off of the block, so I added these two L-shaped reinforcements that essentially clamp onto the motor mount and prevent it from separating from the 3D printed block. After getting all of this done, it's just a matter of attaching the wheels themselves. Just slide each wheel onto a motor shaft and tighten the set screw on each universal mounting hub with the included Allen key. Now the wheels and motors are fully installed and ready to go. At this point, there's only one more mechanical thing that we need to do before we can start with the fun part, installing the electronics. It turns out that the brush roll module is what holds the dustbin in place, and that the dustbin will just fall out now that the brush roll is gone. I solved this problem by 3D printing these two grooved blocks and gluing them into the dustbin area. Now we've got the bin held in place, and we don't have to worry about it falling out while the robot is in operation. With that, all of the mechanical stuff is done, so let's get to the electronics. While the electronics for this project may look complicated due to the limited amount of space, they're actually pretty simple. Here's a full schematic of all of the circuitry, and a higher res version of the schematic can be found in the description. The motor controller, which I hot glued in the right side of the electronics bay, is a Cytron MDD-10A. I really love this thing because it can control two motors up to 10 amps each. It's really cheap, and it even has buttons on it that you can use to test your motors without hooking up any sort of input signal. On the left side of the bay, I've glued in an Arduino Mega with an Adafruit Music Maker shield stacked on top to play the screaming sounds. Make sure that you attach your Arduino with the USB port pointing toward the back of the Roomba so that you can easily connect it to your computer by just removing the dustbin. To the left of the Arduino, we have a buck converter that reduces the voltage from the battery to something that's compatible with the Arduino's VN pin. At full charge, the battery puts out 12.6 volts, but the Arduino website recommends not supplying the board's built-in regulator with anything over 12 volts to avoid overheating it. While this buck converter is probably not necessary here, I just wanted to be safe. Over in the left wheel well, I have a Redcon CM703 DSMX receiver that I can use with my Spectrum DX6 remote to drive the robot around. If you either have a transmitter that communicates on a non-DSMX protocol, or you just don't have one at all, make sure to get the appropriate receiver or just omit it entirely if you don't care about driving the robot around manually. Finally, we have a 2200 mAh 3-cell lithium polymer battery in the Roomba's battery compartment to supply power to the entire device. Now that you're familiar with all the electronics, let's go over the connections in more detail. Remember, there's also the schematic in the description if you prefer to follow that instead of listening to me ramble. Power from the LiPo battery comes in through this XT60 connector that passes through the same hole in the battery bay that the bump sensor wires come through. These wires go straight into the green terminal block on the motor controller that provides power to the motors. Make sure to get the polarity right or you'll let some magic smoke out of lots of components. Each of the black terminal blocks next to the green one connects to one of the motors. The left one connects to the left motor and the right one connects to the right motor. If one of your motors is running backwards after you get everything set up, just swap the two motor wires around and it should start turning in the right direction. There are also two other wires coming out of the green power terminal block that supply power to the input of the buck converter. The positive and negative outputs from the buck converter go to the Arduino's VN pin and the Arduino's ground pin, respectively. Make sure to power up the buck converter and adjust the potentiometer to get the output voltage below 12 volts before hooking it to the Arduino. Additionally, we have two wires running from the Arduino's 5V and ground pins to the 5V and ground pins on the RC receiver. On most receivers, the bottommost pin on each channel is ground, and the middle one is always 5 volts. That's all the power delivery connections out of the way, so now we can focus on the actual communication signals between the various devices. Before we begin with that, make sure that you put solder bridges across the 3 SPI pads on the Music Maker shield, as well as across the pads labeled plus 12 decibels, which enables the shield's internal amplifier that will drive our speaker. With that out of the way, let's look at the connections to the bump sensors. Hook one wire from each sensor to ground, connect the remaining wire from the right sensor to digital pin 22, and hook the remaining wire from the left sensor to digital pin 23. Now let's look at the 3 buttons that change the operating mode of the robot. I've connected the top pins of all the buttons to ground, and I've soldered wires to one of the bottom pins on each of the 3 buttons. From left to right, connect these wires to digital pins 14, 15, and 16 on the Arduino. Now it's just a matter of connecting the speaker, RC receiver, and motor driver to the Arduino. The speaker is really simple. Just screw the 2 speaker wires that we prepared earlier into one of the terminal blocks on the Music Maker shield. I screwed mine into the terminal block for the left channel, but it really doesn't matter which one you choose. Now onto the RC receiver. Connect the throttle signal on your receiver to Arduino digital pin 20 and the elevator signal to digital pin 21. Some receivers will label the channels as channel 1, channel 2, and so on instead of giving them names like elevator and throttle. If this is the case, channel 2 is usually the elevator and channel 3 is usually the throttle. Next, start connecting the motor controller by hooking the ground on the motor controller's header to ground on the Arduino. Finally, connect the signals DIR1, PWM1, DIR2, and PWM2 on the motor controller to digital pins 26, 44, 28, and 46 respectively. With that, we're completely done with the electronics and we can move on to the software side of things. This is the Arduino sketch that brings the Screaming Roomba to life. For the sake of time, I'm not going to go over how it works, but I've heavily commented all of the code in case you're interested. There are a few user configurable options in this section of the code that you can modify to change the speed of the robot in each speed mode and modify how far it turns after a collision, among other things. Before we upload the code to the board, open the Library Manager and install the Cytron Motor Drivers library as well as the Adafruit VS1053 library for the Music Maker shield. Then connect a USB cable between your Arduino and your computer, select the Arduino Mega from the board menu as well as the correct serial port, and upload the sketch to your Roomba. Our final step before testing the Roomba out is to set up the SD card that will house the sound files. Plug a micro SD card into your computer and make sure that the card is formatted as FAT32. Then copy the contents of the SD directory found in the zip file in the description over to the SD card. The sound files in the root directory of the card are the alerts that are played to the user when changing modes, such as going from autonomous to RC mode or increasing speed from slow to medium. Of course, you can record your own alert sounds too, but make sure their file names are identical to mine or else the code won't be able to find them. Put all of your kid-friendly pain sounds in the kid folder and all of your adult sounds in the adult folder. These sounds can be named whatever you want, but make sure that they're MP3 files and that each file name is no longer than 8 characters. I've included some sample sounds in each folder, so you can just stick with those if you don't feel like making your own. While my adult mode sounds are actually pain sounds, I haven't gotten around to recording anything for the kid-friendly mode yet, so I just put Macintosh startup and crash sounds in that folder. Now eject your SD card and insert it into the Music Maker shield. Plug in your 3-cell LiPo battery, put it in the battery bay, screw the bottom cover back on, and now your Screaming Roomba is ready for use. When started up, the Roomba defaults to RC mode and will play sounds out of the adult folder. The default speed is set to slow, but this is only relevant in autonomous mode. The leftmost button toggles between autonomous and RC modes. The middle button changes the autonomous mode speed between slow, medium, and fast, and the rightmost button toggles between kid-friendly and adult mode. In RC mode, you control the Roomba using skid steering, so each stick on your RC radio corresponds to the speed of one of the wheels. With a 2200 mAh battery installed, the vacuum gets around 40 minutes to an hour of runtime on a charge, which is more than enough for a project like this. With all that out of the way, here's a quick demo of the robot with voice lines courtesy of my friend Leon.
Motherfucker! God fucking damn it! Fuck!
I hope you found this video to be helpful and entertaining. If you did, please leave a like and subscribe to my channel. As I mentioned earlier, links to the files and parts that I used in this project can be found in the video description. If anyone actually ends up building one of these, please let me know in the comments because I would love to see it. With that, I hope you enjoyed this video and I will see you in the next one.